Good morning, afternoon, or evening, depending on your time zone. My name is Ellen Mantis. I'm the Director of Science at the Health Effects Institute in Boston. I want to welcome everyone to this webinar on a newly released report from HEI entitled Mortality, Air Pollution Associations in Low Exposure Environments by Michael Brauer and colleagues. This study is one in a series of studies that were funded in response to needs of our sponsor community for better information on health effects at low concentrations of air pollution. For those not familiar with HEI, HEI is a nonprofit independent research organization that provides high quality, impartial, and relevant science on the health effects of air pollution. HEI typically receives balanced funding from the U.S. Environmental Protection Agency and the worldwide motor vehicle industry, and we also receive funding occasionally from private foundations. In the webinar today, you will hear from the investigators, Dr. Brauer and his colleague, Dr. Rick Burnett, who will highlight some of the important findings from their study. You'll also be hearing from members of the HEI review panel for the study, Dr. Sarah Dyer and Benjamin Barrett, who will provide some additional insights on the research. As with all HEI studies, this study underwent an intensive peer review process. This peer review panel that reviewed this report prepared a commentary on the study that you can find on our website. I will be co-hosting this webinar today with Dr. Sverre Vidal, who is Professor Emeritus in the Department of Environmental and Occupational Health Sciences at the University of Washington School of Public Health. He is a pulmonary physician and an epidemiologist with research interests in the adverse health effects of community air pollution and in occupational lung disease. Dr. Vidal chaired the peer review panel for this study. Please note that this webinar will be recorded. There will be an opportunity for a few clarifying questions after the investigators present, and then there will be more time for questions and comments after the review panel's comment. Audience members will be muted, and we ask that you put your questions in the Q&A box rather than the chat. So please use the Q&A box for your questions or comments. Now, before we begin, we are going to hear from Dr. Eva Tanner, who will provide some background on why we want to study the health effects of low levels of air pollution and provide some information on the other studies in this series. Dr. Tanner is a staff scientist at HEI. She has a background in environmental epidemiology and has worked with the HEI peer review panel to prepare the review of the study and their commentary. The floor is yours, Eva.
Thank you, Ellen. So today we'll be discussing why we are interested in studying the health effects of low levels of air pollution in HEI's low-level research program. Ambient air pollution levels have decreased over the past few decades in many high-income countries. And despite this accomplishment, in the 2010s, several studies reported associations between adverse health outcomes and long-term air pollution exposures at levels below the then current air quality standards set by the US, Canada, and World Health Organization. Despite accumulating evidence, there was still limited information on the exposure response functions, particularly at lower exposure concentrations. Recently, the air quality standards have been set even lower. Yet there remain critical questions to answer for ambient air quality risk assessment and regulation. These include, at what level of ambient air quality should the ambient air quality standards be set, and at what level of exposure should we estimate the health effects and the benefits of a further reduction in our air pollution. In 2014, HEI issued a research funding announcement soliciting applications that would help answer these questions. The overall objectives of the RFA were to assess the health effects of long-term exposure to low levels of ambient air pollution, namely all-cause and cause-specific mortality and morbidity, to investigate the exposure response functions for PM2.5 and other pollutants at low levels, and to develop statistical and other methods to improve these assessments. HEI selected 3 studies for funding. Key features of these studies included large populations with millions of people in the US, Canada, and Europe, high-quality exposure assessment models using data from satellites, ground-level monitors, other sources, and modeling, and the development and application of novel statistical methods, including causal inference and nonlinear modeling. The first study was led by Bert Brunekreef of Utrecht University. The study included a consortium of administrative and traditional cohorts across 11 European countries, totaling 28 million people. For context, average PM2.5 levels were 15 micrograms per cubic meter. The second study was led by Francesca Dominici of Harvard University. The cohort was comprised of 68 million older Americans enrolled in Medicare, a national health insurance program. In the US, average PM2.5 levels were 11 micrograms per cubic meter. And the third study was led by Michael Brauer of the University of British Columbia. The census-based cohort included 7 million Canadian adults. This cohort experienced the lowest levels of air pollution of all three studies, with average PM2.5 levels of just 7 micrograms per cubic meter. And of course, we want to acknowledge that the investigators were supported by large study teams with members from many different institutions. To ensure the highest quality research, HEI employs an intensive study oversight and review process. Studies were overseen by an independent committee of experts who regularly reviewed study progress and provided feedback to the investigators. The investigators were required to submit biannual progress reports, annual requests for contract renewal, and were also asked to give webinars and presentations at HEI annual conference. A third-party auditor was also contracted to perform quality assurance and quality control audits of the studies. The final reports then underwent an intensive review process from a separate independent panel of experts who also helped prepare the commentary published along with each report. The Brunekreef report was published in September of 2021. They developed new exposure models for PM2.5, black carbon, NO2, and ozone across Europe. Health data from 11 European countries was used to analyze a pooled cohort of 15 well-characterized traditional cohorts and 7 separate administrative cohorts. Both of these approaches showed that PM2.5, black carbon, and NO2 exposures were associated with natural cause, cardiovascular, respiratory, and lung cancer mortality. They found increased risk for natural cause mortality at even the lowest observed concentrations of PM2.5, black carbon, and NO2. The Dominici report was published in February of 2022. It developed exposure models for PM2.5, NO2, and ozone across the contiguous US. It used a Medicare claims data from 28 million older Americans and applied 3 newly developed causal inference approaches, as well as 2 traditional regression approaches. All of these approaches consistently showed that PM2.5 and NO2 exposures were associated with increased risk for all-cause mortality, and larger effect estimates were observed at the lowest PM2.5 concentrations. And for today, we will learn about the Brauer report, which was published last month. They used a census-based cohort of 7 million Canadian adults and developed annual exposures for PM2.5, NO2, and ozone. They employed a traditional linear-based regression approach and 3 nonlinear modeling approaches. I will now pass the floor back to Ellen.
Thanks, Eva. We're now going to hear from our investigators who are going to provide an overview of the study. I'll introduce both of them now and they'll do their presentations. Dr. Michael Brauer will present first. He is a professor at the University of British Columbia School of Population and Public Health and the principal research scientist at the Institute for Health Metrics and Evaluation at the University of Washington. His research focuses on how the built environment affects human health, with specific interest in air pollution related to transportation and biomass combustion, the global health effects of air pollution, and relationships among multiple exposures. Dr. Rick Burnett will then follow Mike, and he is a senior research scientist at Health Canada, where he has been working since 1984 on issues related to environmental risk assessment. He is also an affiliate professor at the Institute for Health Metrics and Evaluation at the University of Washington. His interests are in mathematical and statistical methods to track health risks from environmental hazards in both time and space. The floor is yours, Mike and Rick.
Thank you for the introduction, Ellen, and thank you for the opportunity to speak to you today. Before I get started, I'd like to just acknowledge that I am speaking to you today from the unceded territories of the Squamish, Tsleil-Waututh, and Musqueam peoples, and I'm grateful for the opportunity to live, work, and play on these lands. I'd also invite you, wherever you are in this world that we all share, to acknowledge the land you are at this moment. So I'm going to present to you an overview of the MAPLE study that we've conducted in Canada, and then Rick Burnett is going to follow with some details on our work to try and understand the shape of the relationship between air pollution and mortality, which is really the primary goal of our study. We were really fortunate in this study to take advantage of some unique linked data that we have in Canada, and in the context of both a national survey called the Canadian Community Health Survey, which is provided to a subset of the population. It's a voluntary survey, but is nationally representative. And it has multiple cycles. In our analysis, we included over 500,000 individual respondents through the baseline years of 2001 to 2012, so multiple cycles of this survey. This provides us a rather small, although it's still 500,000 number of individuals, but a lot of depth, where in the case we have self-reported individual level information on a number of health behaviors, for example, diet, physical activity, alcohol consumption, and smoking. This was complemented with 3 census-based cohorts. These are completely nationally representative. These are the 20% of the population that that is required to complete a long-form census. And so this is entirely representative of the population. These data were linked to death registry and tax records. So tax records give us residential history on an annual basis, which we can then use to estimate exposure over different time windows. In addition, for both cohorts, we have many socioeconomic covariates at the individual level. So the CanCheck cohorts, these census-based cohorts, really provide us size and representation of the population. In the presentation today, I'm mostly going to speak about what we call a stacked cohort, where we've taken these 3 cycles, so a baseline year of 1991, 1996, and 2001, removed any individuals who happen to be so unlucky to have to fill out the long-form census twice, and have a unique cohort then of about 7.1 million subjects with up to 25 years of follow-up. So these 2 cohorts really complement each other. One is very deep, and one is very large and completely representative of the population. An important aspect of the MAPLE project was our exposure estimation. We also are unique in Canada in that most of the country lives in locations of very low concentrations of air pollution, and our focus is on PM2.5 air pollution. And so we put a lot of emphasis on trying to develop accurate exposures, both spatially and temporally, for the entire population, including populations living in rural areas or small communities that have no ground-based monitoring. In order to do that, we worked very closely as part of our team with Randall Martin's group, who was at Dalhousie University when this started, now at Washington University in St. Louis, who has for many years been developing these geophysical approaches using satellite-based information to estimate surface concentrations of PM2.5. In our project, we took an additional step by actually collecting direct measurements of aerosol optical depth from the ground, which is the same metric that satellites use from space, co-located with ground-based monitoring of PM2.5 at 5 locations across Canada. And this allowed us to basically refine the satellite-based estimates of PM2.5 surface concentrations for the low concentration exposure setting of Canada specifically. So we were interested in developing these relationships between aerosol optical depth and surface PM2.5, and we evaluated that and refined that by actually making these direct measurements across sites in Canada. And as you can see from this slide, the composition and the mass concentration varies across the country, as one would expect. And especially this composition is affecting that relationship between aerosol optical depth and surface concentration, so mass concentrations of PM2.5. So we use this to actually improve this estimation and really tailor it to our particular setting. And this is just showing you between the phase 1 MAPLE report, and I'll provide some information on what that actually means, and the phase 2 where we actually implemented this refinement. On the right-hand side is the refined exposure assessment compared to ground monitors across North America. We see an improved correlation and a reduced root mean squared standard deviation now of 1.5 micrograms per cubic meter. So we have a rather accurate and precise estimation of PM2.5 concentrations based on this methodology. We've also applied a backcasting approach where we take historical measurements and use them to push back these spatial estimates prior to the period when we actually had satellite based monitoring globally, and which allows us to get 10 years of exposure prior to the earliest entry of any of the cohorts, which was 1981. You can see from this plot how the concentrations have changed over time in Canada as we move to the follow-up in this cohort. So we're seeing reduced concentrations in the northeast years. So our phase 1 report, where we presented a webinar on this several years ago, we focused on non-accidental mortality for each of the specific cohorts, so the specific waves of the CanCheck cohort and the Canadian Community Health Survey, CCHS. And we also had a pooled estimate across the CanCheck cohorts, where we saw a hazard ratio of 1.05 for a 10 microgram per cubic meter increase in PM2.5 for non-accidental mortality. We applied directed a cyclic graph-driven modeling framework, and we moved from models of minimal adjustment to a fully adjusted model. In that work, we also evaluated sensitivity to the exposure window, so looking at 1 year exposures all the way to 10-year exposures. We looked at varied spatial resolutions, 1 kilometer to 10 kilometer, as well as different resolutions for different segments of the population to account for different differential mobility by age. We looked at sensitivity to NO2, to ozone, and OX, which is a weighted sum of nitrogen dioxide and ozone, weighted by its oxidant potential. And we looked at an indirect adjustment approach for missing behavioral covariates in the CanCheck, the large census-based cohorts. What we found in that analysis is that our effect estimates for PM2.5 were attenuated by ozone and this OX metric, but not by NO2. We found increased hazard ratios with longer averaging time. So as we moved from 1 year to 10 years, and as we went to more finely resolved exposures, so from 10 kilometers down to 1 kilometer. There was also little impact of indirect adjustment for missing behavioral covariates. And we also did a specific analysis focusing on the comparison between immigrants and non-immigrants within Canada. And this is because immigrants, recent immigrants to Canada tend to cluster in urban centers, which we know have higher levels of pollution, but immigrants are also selected on factors including their prior health, so tend to be healthier than the non-immigrant population. What we found, however, was the effect of air pollution was similar on immigrants and non-immigrants. So building on those results in phase 2, and what we'll focus on today is looking at cause-specific mortality and this stacked cohort where we're actually combining the waves of the CanCheck census-based cohorts in a single analysis. I'll only be presenting fully adjusted models, and we'll look at more detail at sensitivity to co-pollutants and regional variation. We used a refined 10-year moving average exposure. So I already mentioned the refinements based on our measurement campaign, where we're focused on a 10-year moving average that is lagged 1 year, and with the resolution of 1 kilometer for PM2.5, 10 kilometers for ozone, and 100 meters for nitrogen dioxide. So just starting out very briefly with the Canadian Community Health Survey, this more deep cohort. This is actually one of the largest analyses of PM2.5 and mortality that includes individual level behavioral risk factors. We have over 50,000 deaths from non-accidental causes and up to 15 years of follow-up. And also, as is common through all these analyses, a very low average PM2.5 concentration, space 6.8 micrograms per cubic meter. In our model, we see a hazard ratio of 1.12 per 10 microgram per cubic meter increase at PM2.5. When we add the behavioral risk factors to that model, we see a slight attenuation of the effect estimate, but still very much elevated. If we move to the CanCheck analysis, so now this is the stacked cohort of 7.1 million individuals, 128 million person years, over 1.5 million deaths, and up to 25 years of follow-up. You can see we have an elevated hazard ratio also for non-accidental mortality and for the specific causes of death. So this is driven, this non-accidental mortality hazard ratio is driven by the major causes of death in Canada, so cardiovascular causes, cerebrovascular causes, and respiratory causes. I will note that while we see elevated hazard ratios for most of the causes that we evaluated, we did not see an elevated hazard ratio for lung cancer, which is somewhat a surprise and remains unexplained to this date, and also for kidney failure, which is an outcome that where there are some studies showing some relationships with PM2.5. Rick will go into this in much more detail, but this is just some information on the shape of this concentration response relationship. We applied a very exhaustive approach to look at trying to characterize this shape. The results that I presented to you earlier were all for linear models, and start at the upper left-hand corner. That can be reasonably approximated with a spline there with just 3 knots. But we looked at a very large number of knots to try and better characterize this relationship. And I'm only showing some of them here. I think we went up to 18 knots, and we selected the best fit with the based on the Bayesian information criteria, and this is the one that is highlighted in red. It's a relationship with 9 knots. What you can see in that, and I'll come back to this, is that we see a rapid increase from the lowest concentrations in our cohort, which is at 2.5 micrograms per cubic meter. Then there's a flattening of that relationship, and then another increase above a concentration of 9 or 10 micrograms, 8 micrograms per cubic meter, and then sort of another flattening of that relationship. And we're only able to see this when we use multiple knots. In this case, 9 knots is our best fit. So this is actually rather puzzling. What is going on in this sort of middle range? Why would we see a rapid increase, sort of a flattening, and then another increase? So we investigated this in more detail. One of the possibilities is to look at the effect of co-pollutants. I mentioned earlier in our phase 1 report, we did see attenuation of the effects by ozone, and this OX measure, this weighted sum of ozone and NO2. We saw the same thing in this stacked cohort analysis. We saw an attenuation by ozone and greater attenuation by OX. And when we look then at actually this is now looking at the shape of the relationship by tertile of ozone on the upper panel and OX on the bottom panel, we see really only at the highest tertiles of ozone where we see a relationship for PM 2.5 and non-accidental mortality that really shows a consistent increase. So it seems as though the effect of PM 2.5 is somehow dependent on the level of ozone or OX in this case. And so for the low tertiles of ozone or OX, while we still see some indication of increasing hazard ratios, it's really quite a complex relationship. We also did an analysis where we removed individuals who had exposures above 12 micrograms per cubic meter or above 10 micrograms per cubic meter. And I'll point out that this means that this is their 10-year average, so above 10 and above 12. And when we restrict these analysis, we still see increased hazard ratios, but they are somewhat attenuated. I will point out that this means that we're actually not, these aren't direct comparisons because of course these are different participants. So we, while we're just selecting based on the concentrations, there's also differences in the populations and where they may be regionally in the country. We still see, however, in both these cases that we see a rapid increase, again, from the minimum concentration of 2.5 micrograms per cubic meter, and then a flattening of the relationship in both of these restricted cohorts. But this analysis does give us some suggestion of increased hazard ratios, even at lower concentrations. So individuals who've never experienced concentrations above 10 micrograms per cubic meter. To further investigate this complexity in the shape, we decided to look at how the relationship between PM 2.5 and non-accidental mortality varied regionally across the country. And so we split this, we split the country up into airsheds, which had been developed prior to the analysis. So this is actually based on our understanding of meteorology and the topography in Canada. And what you can see here is that there's 2 airsheds in the country where we actually really don't see any relationship between PM 2.5 and non-accidental mortality until we get to very, very high concentrations. So all the other regions, we still see this rapid increase. We're in very low concentrations, and some suggestions of flattening. But in these regions, we actually see nothing really going on until rather high, well, high in the Canadian context, high concentrations above 10 micrograms per cubic meter or so. So what we're seeing is regional variation in our hazard ratios. We did quite exhaustive analyses to try and rule out differences in any population characteristics or demographics, looking at the age of the population, the proportion of immigrants or indigenous populations, healthcare access, and we really did not find that any of these could explain these differences. So we're left with the possibility that this is actually due to differences in air pollution source makeup and the mixture that individuals experience within these different air sheds. And this may relate also to the prior results that I showed you with the influence of ozone or oxidant potential and how those influence the shape of the relationship. So just to wrap up, what we're seeing is consistent associations between PM2.5 concentrations and non-accidental mortality in all cohorts, including the stacked cohort of 7.1 million Canadians. It's population representative, and our results suggest that these are unlikely to be confounded by behavioral risk factors based on our analysis of the Canadian Community Health Survey. We have very low levels of exposure, a minimum effect level of 2.5 micrograms per cubic meter over a 10-year mean. So again, very, very low. And these associations are driven by the major causes of death that occur in Canada: cardiovascular disease, stroke, and respiratory causes. And I'll point out again that we did not observe an association with lung cancer. These associations varied regionally and were attenuated by ozone and oxidant potential, and they're unlikely to be, this regional variation is unlikely to be due to population characteristics. So again, our thinking is that this is likely driven by differences in pollutant mixtures. We found consistently no evidence of a threshold and in general a supralinear shape of the relationship. So implications of this are that there should be continued benefits of continued reductions in exposure to PM2.5 concentrations below what the levels of many national standards and even below the recently updated World Health Organization guideline of 5 micrograms per cubic meter annual average. And I'll just show you very briefly some implications based on the refined global concentration response function, where we've taken the results from our analysis over the 2.5 to 5 microgram per cubic meter range, and basically extended below the World Health Organization guideline and what that might mean for global mortality. So what we've done here is in yellow is estimates of attributable deaths based on basically the WHO guideline, where we were saying that between concentrations of 2.5 micrograms per cubic meter and 5, we really don't know what the if there is an increased hazard ratio. So we're sampling from a uniform distribution between 2.5 and 5 as our counterfactual concentration or no effect level. And then in the blue, what we're doing is we're actually applying the shape derived from our analysis over that range. So now we're saying we actually do have information between 2.5 and 5. And what we can see is that we shift the distribution, we increase the number of attributable deaths annually, adding more than 1.5 million deaths globally, which is a 17% increase based compared to the baseline, which is a global concentration response function that Rick has actually developed. Where are these additional attributable deaths occurring? Well, they're occurring primarily, as one would expect, in mostly high-income countries. So again, suggesting that this work provides information that there may be continued benefits, especially in these rather low exposure settings, which tend to be in the high income countries of the world. So with that, I would like to just acknowledge everybody on the MAPLE team. It was really a wonderful team to work with over many years, and really worked very well together. It was really an amazing opportunity. Also would like to thank our partners, the Canadian Urban Environmental Health Research Consortium, for providing some data, as well as the Canadian Research Data Center Network, which allowed us to do some analyses in a distributed fashion, and certainly HEI for supporting our work. So thank you, and I will turn it over to Rick.
Okay, just hold it here. Okay, well, thank you, Mike. And so Mike presented some very interesting spline fits. And what I like to talk about is, in certain situations, we would like to use that information to produce concentration and response models that we think are suitable for mortality benefits analysis, like the analysis that Mike presented at the end of his presentation on global implications of how the low dose shape impacts mortality estimates around the world. So why are we interested in the shape of the concentration response function? Well, I think there are two sort of general areas. One is for input for standards and guideline settings. And that is, I think, a lot of the motivation for these low exposure projects. We've tried to identify the range and concentration, usually at the low end, where we are or less certain if a change in this case, mortality risk exists. We fit classic threshold, so-called hockey stick models to do that. We've also restricted exposure below selected concentrations. And all three groups have now applied in a new harmonization project funded by HEI, causal inference methods developed by Francesca and her team. I like to really focus, though, on the second major area, which is burden benefits analysis. In that case, we want to calculate population health impact associated with current air pollution exposure compared to some kind of policy relevant background or standard guideline. So we're thinking of taking current exposures and all the way down to very low levels. And I call that a burden analysis. And for instance, in the Global Burden of Disease, we publish that type of analysis annually. The other interest is in marginal changes in exposure to some specific strategy to improve air quality. And so people come up with a large number of strategies. They estimate changes in pollution exposure, often through chemical transport models. And some of these changes can be very, very small. And in that case, we're interested in how that marginal change anywhere in the concentration range is going to affect a marginal change in health benefits. And in that case, we actually want to characterize both the magnitude and the shape of the concentration response association through the entire relevant concentration range. And we've done this, and it's historically been done for concentration response functions from representative single cohorts. So for instance, the American Cancer Society cohort in the US, CanCheck cohorts in Canada, different cohorts in Europe have been used specifically in those jurisdictions where those subjects have been living. The benefits calculation is quite simple. It really is the benefits between Z sub C, a current exposure, and some kind of future exposure. And that's equal to the population, the target population of interest, the disease incidence rate, and the population attributable fraction, which is given by 1 minus 1 over the risk at the current concentration divided by a future concentration. So what we're particularly interested now is what does this R function with concentration look like? Well, the most popular model is the log linear model, which says the log of this risk function is a linear function in concentration with some slope beta. And the population attributable fraction then looks like this. And in particular, it's the estimate of beta at the current concentration minus the estimate of beta at a future concentration. And what is typically done is the parameter estimate is obtained from the cohort study, published literature, usually has a normal distribution with some mean and standard error. And what's normally done is about 1,000 of these realizations are created. That creates 1,000 values of the PAF, and that is the uncertainty distribution that feeds into the burden analysis. For the burden estimates, we often set the future concentration to something called a counterfactual, which is often a relatively low concentration. So in our modeling efforts, we're really interested in modeling the relationship between the risk at any concentration and that at something at a very low concentration. Well, we started a project called the Shape Constrained Health Impact Function, and which we created a bunch of transformations of concentration that look sublinear, superlinear, and sigmoidal shaped. And we would fit those transformations to the cohort data and estimate this unknown slope parameter theta. So this was like the log linear model. It was extending almost exactly the log linear model to nonlinear models. And we applied this to 15 cohorts, some of the largest cohorts around the world. And these are the kind of shapes and uncertainty we were getting. And most of them were clearly nonlinear. So it really appeared in these cohorts that the linear model assumption was not a robust assumption. And we pulled those together, which formed the global mortality exposure or GEM model published in PNS in 2013. Well, there was some limitations of this method in that how many of these transformations could you form? And if you wanted a complete characterization, would you have to form thousands and thousands of them? So what people tend to do now is they tend to like to use spline models in benefits analysis. And that is they want to use a spline representation of the PAF, which is now replacing this difference from the log linear model with differences in spline predictions. But what happens if that spline fit is not well behaved? So in the shift analysis, when we created these transformations, we made it such that they all looked nice, and whatever the results of the cohort analysis were going to be, we felt that they were all useful for benefits analysis. But when you fit a spline, especially an unrestricted spline, you can get some very wiggly shapes and some shapes that you may not want to directly use, as Mike had presented with the Kanchek cohort. Well, you can restrict the spline fits. You can make them monotonically non-decreasing, but sometimes you can end up with little plateaus in the fit that you might not be too happy with. You can make them sublinear. You can make them concave and increasing superlinear, and we're now using a smoothing spline in the integrative exposure response model with the global burden of disease. And to get sort of reasonable fits of that data, we restricted the spline fit to concave and increasing, which produce superlinear fits. But for any single cohort, I mean, are really these constraints a little too simplistic? They certainly don't cover sigmoidal shapes, which cohorts can certainly have, and they may not really be able to identify a threshold pattern over low, sort of narrow and low concentrations, which we may be interested in. So here's the spline fit of the 2001 Kanchek cohort. So this is just one phase. This, I would suggest, is a very nice looking spline fit. I would certainly use it in a benefits analysis. And one of the things that people like to do is they like to represent the relative risk or the hazard ratio at the minimum concentration to be equal to 1. These splines have a characteristic that the confidence intervals increase as you get away from the mean. And when you fit the minimum concentration hazard ratio to 1, the lower concentration, lower confidence limit will always be less than 1. So you might want to think that in this case, there's some small range in concentration in which you're going to get unclear estimates of benefits. But here, what I plotted at the bottom is the population attributable fraction for a very small change in concentration, which is basically the derivative of the PAF. And this is really the function we're using in benefits analysis. And you can see here that the uncertainty intervals are all above 0. And so what you're really seeing is that the upper confidence limit and the lower confidence limit are both increasing of the spline prediction. However, here's a spline prediction where we've now adjusted for ozone. So as Mike suggested and pointed out, that when we control for ozone, the PM2.5 effects go down. So now we get this nice sublinear association. We see now that the upper confidence limit is decreasing, and that means that the upper confidence limit on the relative risk function is, of course, the lower confidence limit on the PAF, because it's a function of the inverse of the relative risk. And now we can see that we're getting uncertain benefits. We're getting positive and negative benefits at these lower ends. So we want, whatever way we're going to characterize these functions, we want to actually be able to characterize uncertainty in this manner. So here is the plot of the best fitting restricted cubic spline for the CanCheck cohort. You can see it has an initial rise, very steep rise. It has a sort of plateauing out. And this is over a wide concentration range. And then it's generally sort of going up with maybe a small decrease at the top. So if we fit a monotonic spline to this, I think we might be concerned that we might get a plateau in a place like this, because you can see the confidence intervals are very small. Now here is a smoothing spline. So this is a smoothing spline of the Medicare cohort as part of the harmonization project between the 3 different studies. And I'd like to thank Francesca for allowing me to present this. And I wanted to present that because regression splines sometimes can be very wiggly and unstable. And you would hope that a true smoothing spline with a penalty function on the second derivative to smooth it out would be smoother. But here you can see we get sort of an oscillation at low concentrations. It's going maybe a little negative. Then we get followed by a very steep increase, followed by a less of a steep increase. So we've got some real complication that's going on here. So the way that we're going to try to smooth that out is through an algebraic function. So this is the shape constrained health impact function. So this was the function that we used in the GEM study. It's basically a product of a logistic function and a logarithmic function. It's restricted to monotonic associations depending on the theta parameter, positive or negative. The logistic models sublinear and sigmoidal shapes, the log models superlinear shapes, and it turns out that the value of the parameter alpha or tau, if it gets very large, the shape becomes virtually linear. And this will cover many of, let's say, but not all 3 segment shapes that are of possible interest. So what we did is we added another logarithmic term that allowed us to cover more shapes of interest. It also allowed us to cover the spline uncertainty. That is, you could have positive and negative uncertainty at certain predictions. However, it does allow protective effects. And this is, of course, one of the big controversial issues in this kind of modeling is, should the spline actually allow protective effects, even if it's based on its uncertainty. These parameters control the curvature. The mu parameter controls the shape, and we do put some constraints on the amount of curvature. So the larger values of delta and alpha produce less curvature. The larger value of tau produces less curvature. We restrict them to be greater than 1, so you can't have any more curvature than a logistic function. And here in this presentation, I'm restricting tau to be greater than 2% of the concentration range. If it gets less than 2%, the logistic function basically becomes a step function at the value of the parameter mu. So here we go back to the 2001 cohort. We fit the shift at the top, left-hand panel. We fit the E shift at the bottom. Both of those look like almost perfect fits. So we've got a really nice stable spline. We're happy with it. Either method works well. Here's the PAF. It looks reasonable. Here we adjust for ozone now. And what we see at the top with the shift is the upper confidence limit is sort of horizontal. And that is, it's not able to fit the declining upper confidence interval where the E shift can. And you can see here what we've done is we've just translated uncertainty with the spline and the E shift being positive and negative at the low end, and we've shifted it over with the shift model to be in the middle range. So basically in these situations, we're not really consistent with the spline fit. Here's a fit from CanCheck. This is ozone, controlling for PM. And this is in the stat cohort. You can see you get this sort of complicated structure to it. Again, you get declining upper confidence limits at the low end for ozone. You can see the shift really isn't modeling that very well, where the E shift actually models it quite reasonably. Here is the CanCheck stat cohort for non-accidental mortality. We can see now that we get a fairly close and reasonable representation of the spline. We model the large increase at risk. We model a plateauing, and in fact, in this model, it's a slightly negative with the lower confidence limits on the PAF being less than 0. So this model does allow negative benefits. We see the middle section is roughly equal to the log linear model, and in the PAF plot on the right-hand side, the horizontal purple line is the PAF of the log linear model. So you can see what kind of differences you get from an assessment of the spline or E-shift model compared to the log linear model. And then we see this sort of fairly large range in concentrations that's declining, and the E-shift is actually trying to take that on a bit. We go to, we could also make the fit positive, so we can restrict the E-shift predictions to be always positive. You can say, well, I'm really not comfortable with negative benefits. And there is the positive restriction. You know, again, it's showing in the middle part, in the middle range, the more leveling off of the change in the marginal risk. Here is the Medicare cohort. Here is the E-shift fit. We can see the slight decline in risk for lower concentrations. The PAF is less than 0 in that case. And then we get this very steep increase in marginal change in risk. So this is about 5 times, the peak is about 5 times the marginal change as the log linear model. So you can imagine if I'm doing an assessment of, let's say, a major point source that might go into a metropolitan area, where I put that point source, because I can have 3 or 4 micrograms per meter cubed change across a metropolitan area. Where I'm going to put that point source is really is going to dictate possibly major differences in the benefits analysis. And then the curve starts to look like more like a linear model at the upper range. And you can see, because the range in this dip at the top is very narrow, the E-shift isn't picking it up. It's only really picking up major features in the concentration. Here's if I make it positive. So you can see here, because of the small constraints on curvature, the function, it just can't jump up really rapidly. So it's actually shifted the peak over a bit. So of course, anytime I constrain a fit, it's going to have a biased prediction compared to an unconstrained fit. And here is a threshold model. So this is a case where you might say, well, let's model a threshold, keep the predictions positive. But threshold models have these really strong limitations for marginal benefits, as they get basically a discontinuity at the threshold. So we suggest shape restriction and health benefits model is desirable for policy analysis. We suggest that oscillations over narrow concentration range should be removed. So I think that's probably uncontroversial. Should negative benefits be allowed, either in mean predictions and uncertainty? And I think that is a really debatable point. Is obviously if spline functions are going to have negative marginal changes in them, we're not going to represent those if we restrict the predictions to be positive. And splines can produce, even though they're smoothing splines and they are modeling smoothness in the second derivative, the curvature of the first derivative still can be very large. And as you see in the cases in the CANCHEC and the Medicare cohort, there are sections here which have very rapid increases in risk. So should we, in fact, restrict curvature? And if so, how are we going to do that? And I'd like to just finish by saying that we caution that the E-shift is not best suited for exploratory analysis of primary data. These unusual concentration response patterns may identify residual confounding, or I think more interestingly, variations in atmospheric mixtures by PM concentrations. That is, large curvature actually may represent changes in low mass particle phase pollutants like transition metals, ultrafines, or oxidative potential that can vary several fold when the PM 2.5 varies very little. And Scott Weisenthal in our group has done a lot of work on this in Canada, where he's shown that you've got almost, between locations can have almost no change in PM 2.5 mass, but huge changes in oxidative potential and transition metals. So this is something that we're very interested going on in the future, is trying to understand that. Thank you very much.
Thank you, Mike and Rick, for those great presentations. We have a few minutes for some clarifying questions. I'll start with one. I think, can you comment on the composition of PM 2.5? Did you estimate how much diesel engine exhaust, elemental carbon, black carbon was contained in the PM 2.5 as a percentage?
Yeah, thanks for that. I'll take that. So we did that in the places where we made measurements, and that so we have a reflectance based measurement of elemental carbon. Across those 5 locations, it varied. It varied anywhere from 4% to about 12%. We also then are working that into the geophysical model. So we actually do have percentages of elemental carbon now across the whole country, and that's something that we're going to be applying in future work, where we're going to be looking at PM composition as well as source contributions and the relationship with mortality.
Thanks. Another question is, what are the implications of these results for countries where PM 2.5 levels are consistently higher?
So I think, we directly are not providing much information, let's say, obviously above concentrations that exist in Canada. So if you're talking about concentrations of 20, 30, 40 micrograms per cubic meter, we tend not to see those in this analysis, although if we would take the understanding that there's a relationship at lower concentrations, we would expect also there would be a relationship at the higher concentrations. But really the focus of our analysis was on these low concentration environments that, as I pointed out sort of at the end of the presentation, really are restricted, fortunately, to a subset of countries, especially high-income countries in many parts of the world.
Thanks. Another question is, were you able to attribute any effects to tire-related particles coming off of tire wear or the road?
No, we didn't look at that directly.
Okay. And I guess there was one question you answered already, Mike, but I think maybe a good question to wrap up here is how generalizable are these results to other countries? And can you comment sort of on these broader implications?
Yeah, so I think we would say that these are applicable elsewhere in again in the sense that what we're seeing is harmful effects of PM2.5 on mortality and on cause-specific mortality at very, very low levels. So we would expect the same to be true elsewhere in the world. I'll caveat that again that we did see within Canada, we saw regional variation, but the locations where we tended to see these I would say less than monotonic, the increasing effects with the increasing concentrations tended to be in more rural areas of the country. So locations where we have primarily urban populations, we saw this consistent relationship. So I think this would translate elsewhere in the world, and again suggests that there should be continued benefits to reducing PM2.5 down to these very, very low levels, so below even the current World Health Organization guideline of 5 micrograms per cubic meter.
Okay, thanks. And we'll have more time for questions and comments after at the end of the webinar. I'll ask Rick, can you stop sharing your screen now? Thank you. And I'll turn it over now to my co-chair, Sverre.
Yes, thank you, Ellen. I'm now going to introduce members of the review panel that'll be providing some perspectives from the review panel on the MAPLE study. The first presenter will be Dr. Sarah Dar, who's Associate Professor and Associate Chair of Epidemiology at the University of Michigan. Her research interests focus on human health effects of air pollution with an emphasis on outcomes of aging and a growing interest in intervention studies. She's served as an expert panelist for the EPA and is a member of the Health Effects Institute Review Committee, as I mentioned. Following her presentation will be a presentation by Dr. Ben Barrett, who's a reader in environmental exposures in public health and deputy director of an environmental research group at Imperial College London. He specializes in evaluation of improvement initiatives, including the London Congestion Charging Scheme and Low Emission Zone, both of which have been used to inform other national and international schemes. His most recent research aims to improve the resolution of environmental exposure assessments for epidemiological studies and methods of public health improvement. So I'll hand it over to Sarah to continue.
All right, and actually, I had sort of thought that Ben was going first. Ben, did you want to take?
Yeah, I'm happy to go first. I think that makes a little more logical. Thank you, Sverre. So, as Sverre said, I'm presenting on behalf of the Low Exposure Review Panel, giving a few short perspectives on the exposure aspects of the MAPLE study that you've just heard about. So you'll have seen some of the figures I'll be presenting previously in Mike's presentation, but from a review panel perspective, we were extremely impressed by the scope of the exposure model created from MAPLE, representing many, many years of work by many different investigators, culminating in this model, which covered the whole of North America. A major strength was the diversity of inputs, particularly 1998 onwards, which is actually going back quite a long way, including the satellite data, the chemical transport modeling, ground-based monitoring and verification, speciation of PM, and validation against an extensive monitoring network. The 35-year time span was extremely long and allowed the incorporation of very, very large volumes of epidemiological data and strengthened the results from that perspective. The multi-pollutant models that were created were principally to test the co-pollutant influence of the influence of the co-pollutants on PM2.5 exposure outcomes, not exposure into themselves. The PM species were also used to help improve those AOD estimations, as Mike explained earlier on. However, there was some mismatch in the spatial scales that the panel noted. The principal model, the PM2.5 model, was at the spatial scale of 1 kilometre. The ozone model was initially at 21 kilometre grid. That was later improved. That was improved in later years to a 10 kilometre grid using chemical transport modelling. The NO2, as Mike mentioned, was at 100 metre grid resolution from a land use regression model. However, it should be noted that that LUR was produced for 1 year, so there was quite extensive backcasting used for the NO2, less so for the ozone because there was multiple years modelled. So those spatial scales were different between the different co-pollutants. So you've seen the figure on the left, figure A, before from Mike's presentation. And this is the performance of the phase 2 model, MAPLE exposure model for PM2.5 across the whole of North America against ground-based monitors 2000 to 2012. So across that spatial and concentration scale, there's a very impressive R-squared of 0.81. And this really represents a pretty impressive feat for a model at that spatial scale. However, the review panel were particularly interested in low exposures, as this was a low exposure study. And again, as this was using epidemiological data in Canada, we asked that the performance of the model be evaluated, truncating at 10 micrograms and just showing Canadian concentrations. And that's what figure B shows. And the MAPLE study team did produce this. You can see that the R-squared is somewhat lower at 0.6. It's still good, but not quite as high as the 0.81 for the full North American model across the full ranges. I think it also should be noted that the backcasting back to 1980s loses some of those valuable inputs the further it goes back. So we would expect the performance of the model to worsen as it goes back in time prior to 2000. However, as Mike also presented, concentrations in Canada have dropped over that timescale, so the majority of those low exposures will be occurring in later years. 50% of all person years in the CanCheck cohort were below 8 micrograms and 25% were below 6. So that level of 10 does represent more than the majority of the population used in the epidemiological results. So the panel found the regional airshed results being particularly interesting and important, and I am encroaching on Sarah's territory here, looking at some of the actual epidemiological results, but it is important from an exposure perspective. Northern Territory, very large, not many people living there. That's only 1% of the study population. And Mike has mentioned that those two regions in the south, the Prairie and the West Central, saw this relatively flat response at low concentrations, contrasting with those seen in the Western and East Central regions. East Central covered the most populous area and 60% of the study population. And that's where you see the rapid increase and then the suggested flattening off. However, we should note the differing y-axes on these relative risk scores. Those two in the Prairie and West Central are higher, discounting the 1% in the northern area. So we've got scales up to 2 there, and that flattening is occurring around 1.01 perhaps in the Prairie region, which actually is not far off flattening out that you get in the East Central region. So you still see a rapid increase between concentrations of 2.5 and 5 micrograms before the flattening off occurs. And then the major difference occurs between 5 and 10 micrograms. The MAPLE study team proposed this to be differences in composition. And this is extremely important as it has implications. First of all, what are the implications of merging these different regional airsheds into one overall response curve? And this, I think, speaks to Rick's final conclusive point there about different metrics and small changes occurring in the transition metals, but very little response to PM 2.5. So the complexity of the overall study response curve for non-accidental deaths may be made complex by those different regional compositions. Secondly, what really is going on in that important region between 5 and 10 in these airsheds? What are we saying to the people who live in those airsheds? That we can't see a change, that there is some protective effect, or is this looking at too much detail into the results? So I think this is important and requires further investigation. And it is really the strength of the model, the size of the model, both exposure and epidemiologically, that allows these important conclusions to be drawn out. Final point is that there are significant overlaps, but also differences in the methodology, exposure modeling methodology of the 3 low exposure studies funded by the HEI in US, Canada, and Europe. So I'm pleased to see that there is a comparison underway between the 3 exposure models, harmonizing the results to see what difference comes out when one study uses an exposure model for another set of epidemiological data. There are overlaps, as I say, so this isn't a truly independent validation. And I think it personally would be interesting to see what bottom-up emissions modeling can contribute to these exposure models in future. So to conclude, the panel felt this was a very impressive effort to create a highly detailed hybrid exposure model for the whole of North America, utilizable for future studies, and I'm sure the model will be used in many different ways. Co-pollutant effects are clearly important as presented by the study investigators, but note that there is spatial mismatch of those models which may limit interpretation. Before all of us exposure scientists pack up and retire, we should highlight there are still exposure measurement errors in these models, particularly in rural areas where there's scarcity of ground-based monitoring. The model performance at low levels is not as good as model performance at high levels. There's still spatial mismatch between where people live and the grid squares, and backcasting is challenging when you're extrapolating results backwards for a significant period of time. That heterogeneity in the regional airshed exposure response curves requires further investigation, particularly if it's chemical composition. We need to get to the bottom of that one. And we eagerly await the comparison of the outputs from the 3 low exposure models. And with that, I shall pass over to Sarah.
Thank you. All right.
As soon as I stop sharing.
Okay, fantastic. Just give me one moment to get my slides up and we'll be good to go. Oh boy. There. All right, you guys see the right view now? Okay, fantastic. Thank you so much. So hello, everyone. Thank you so much for having me here. I'm really glad to present some reflections from the review committee on the epidemiologic side of this report. I will say that I tried my best to gather many of the thoughts and comments from my esteemed colleagues, and I will take any blame for mistakes here and give them credit for the clever thoughts that are in this. So, of course, there we go. All right, so first off, I just wanted to start by saying how much our team really commend the investigators of MAPLE for this fantastic study. It has so many important strengths that have really given us important insights into the associations that we're interested in here, especially at low levels. So starting with some of the things that you've already heard, you know, it really is a huge population. We're talking about, you know, hundreds of millions of person years from a nationally representative sample across Canada. And I thought it was really quite interesting, right, that we are talking about approximately, you know, 20% of the Canadian population is able to inform these questions that we're interested in. You also heard earlier why Canada is such a great place to do this study, and that the concentrations are so very low. And I put up just a nice little graphic that I made here using the new HEI State of Global Air tool, which just came online a few days ago. It's really fun to play with. But I think it really shows us, Canada is the one all the way down at the bottom in yellow. You know, what it shows us is that this population is really uniquely, you know, set up to answer these questions about low exposures. So that's really a wonderful strength of the MAPLE study. The other thing that's really an important strength that we wanted to highlight is the data that they have. So in addition to having this nationally representative sample, there was the information not only on total, you know, non-accidental mortality, but also on cause-specific mortality, which did allow them to provide a bit more insight in terms of biological plausibility, you know, and perhaps into mechanism. There also was the nice information that we heard about on co-pollutants. And, you know, there really is a lot of data on personal characteristics, even within the stacked cohort. So there's information on, you know, income, minority status, education, marital status, employment, you know, occupation, urbanicity, neighborhood deprivation, and all of these features that are there and possible to account for confounding even in the larger cohort. And as you heard from Mike, the additional data set, which had a smaller subsample but had information about, you know, lifestyle characteristics and things like that, also did allow them to do the sensitivity analysis of adjusting for more confounders. And as we heard, you know, there's a little bit of sensitivity for certain outcomes, but overall the findings seemed pretty robust with all of those different adjustments. So those are all really nice strengths about this study. So this is just another graphic. You've seen, you know, the results a few times now, and I just wanted to pause to put the findings of this MAPLE study from Canada, you know, next to the Medicare study, next to the European cohort, to really see how consistent these findings are across the three, you know, low exposure studies that have been funded by HEI. I think it pretty conclusively shows that, you know, there's increasing risk of mortality with increasing concentrations of PM fine, even at these very low levels. I think it's quite interesting that you do see the same evidence of, you know, what we call supralinear relationships with stronger associations between PM fine and mortality at the lowest levels. And as this has been talked about several times, right, because this was really the push of these studies, is it has important implications since we know that the Clean Air Act and other regulations around the world have been successfully lowering concentrations over time. And so this really informs the question of how much added benefit there is to reducing standards even lower, right? And I think compellingly we see that there does seem to be benefit, you know, to reducing levels lower and lower to achieve lower risks of mortality. Now, another thing that the study did quite nicely was all of this effort that they put in, and we heard from Rick, you know, about investigating the shape of the concentration response curve. We heard the different ways in which it was investigated, right? So we heard about the restricted cubic spline that really allowed for very complex curves. We heard about this extended shift model that allows for nonlinearity, but it's more restricted to shapes that are likely to be plausible. And then also this threshold model, which really is trying to get at the impact of, you know, whether or not there's any level at which no effect can be seen. And we also heard, right, that they restricted their sample just by literally clipping the data set to folks who were exposed to levels less than 10 and less than 12. You know, each of these methods has their own strengths and limitations. You know, for example, the committee spent a long time thinking about the shift model since it is new. You know, I think it's exciting, but there were some concerns since it is so new. Some of the statistical properties have yet to be established. Similarly, there was some, you know, thoughts about how you can interpret the threshold model based exclusively on when the confidence intervals, you know, cross the null. But I think overall, one of the really nice things is that each of these methods was presented, right? They each are coming at it from a slightly different angle, and yet they tell a consistent story that at the low levels that we observe in Canada, really all the way down to 2.5 micrograms per cubic meter, you know, there are apparent increase in risk with increasing levels of air pollution outside. And that was true even when you restricted the concentrations again to these very low levels. Now, that of course brings us to the other piece that's been talked a lot about in this call because it was so interesting, is this space between the 5 and 8 micrograms per cubic meter where, you know, the concentration response flattens out. If you're looking at the spline, it gets a bit wavy. And really trying to understand what that means it is quite interesting, because if it's real and there is this flattening at that level, you know, it implies that reductions in that range might not be as consequential. But as, you know, the review committee talked about it and thought a lot about that, you know, we had a hard time believing that there's some sort of biological mechanism that would support that, you know, air pollution less than 5 micrograms per cubic meter is bad for you. Air pollution, you know, over 8 micrograms per cubic meter is bad for you, but there's something magical about that 5 to 8 that biologically wouldn't matter. So that didn't seem to be very plausible for us. You know, it also was noted that it's inconsistent with the rest of the literature, that there's sort of this magical space in the middle of the distribution of exposure that is, you know, totally safe. So instead, you know, we spent time thinking about what other explanations might be. As you can hear, the investigators obviously spent a great deal of time thinking that as well. Initially, we talked a little bit about whether or not it could just be overfitting of the data because there's so much data in this cohort. But that was not really thought to be the most likely explanation, because lots of data gives you, you know, precision, but it shouldn't really influence the actual point estimate. Of course, it does allow it to be more wavy, but you know, we thought that there might be something real underlying that space. You know, there was, as Mike told you, there was a lot of efforts by the investigators to adjust, you know, for various characteristics like medical care spending and place, and it didn't remove the phenomenon. And so, you know, we, like the investigators, thought that it could be due to these, you know, differences that they observed in airsheds. So again, this slide I actually modified from Ben, but right, it is again showing you this phenomenon that we've seen a couple of times of the Prairie and the West Central having that flattening of the curve that isn't necessarily seen in the other airsheds, which could support that, you know, there was different, you know, composition or sources in these areas at that range that might be changing the concentration response. There also was a thought among the committee that it could have something to do with the population. So not so much from a confounding perspective, but perhaps, you know, there are certain individuals in those areas who have, you know, lower susceptibility or greater susceptibility to air pollution for various reasons that could potentially, you know, account for that sort of unique flattening in the 8 to 5 range. So with that, you know, like the other speakers who have come, I think, you know, our thought was that It's really intriguing, those different associations by airshed and in that middle range of 5 to 8, which really tells us that future work is probably warranted to understand, why we see this unique concentration response, trying to get to the bottom of it. Could it be certain sources or certain components that are driving that? But overall, I would just say that, the review committee felt that this was very much a well-conducted study. It provides a lot of information with its large study size and nationally representative cohort from Canada at very low levels. And we really did see that the findings, indicated that PM fine in outdoor air does indeed seem to increase mortality, even at the very low concentrations. And it might be that it's stronger at lower levels. So with that, I am going to wrap up and pass the baton back.
All right, thank you, Sarah and Ben. I'm now going to throw the discussion open to the wider audience, and we already have a series of questions that have been posed to the investigators and panel, and I'll make my way through these. One may have been addressed already, but I'll ask it again, and it's an important one relating to the wider policy implication of the results, and specifically how achievable realistically reducing these very low PM 2.5 concentrations are. So, what advice should one be given to protect public health given that difficulty?
So thanks, Ray. I'll take a stab at that. So my interpretation of these results are that it suggests maybe a move away from the approach that has been used, which is setting a numeric standard that you should meet or not meet, but rather moving towards an approach of continuous exposure reduction. So wherever you are, you have a goal of next year reducing by 5%, and after that reducing by another 5%, and just pushing the limits as low as possible. In terms of achievability, obviously that's going to vary by location, and by airshed, and has that additional challenge now in a warmer climate where we're getting more atmospheric production of secondary pollutants and things like wildfire smoke. We do have populated parts of the world with concentrations, let's say around annual averages of around 4 micrograms per cubic meter. That's still in a world with combustion sources. If we think about a decarbonized world, it's possible probably to push that even lower. So, but again, I think the implications are really, I would suggest to move away from this fixed numeric standard and rather move towards a model of continued reduction. I don't know if Rick wants to add more to that.
Sure. Well, I think that, if you look at it from a benefits assessment point of view, I mean, even in the United States now, the population weighted average exposure is around 8 micrograms per meter cubed. We had this debate in the US about whether one should actually count benefits of reductions in pollution below the standard of 12. And so when you think about assessments of, fuel additives in automobiles, which would then impact reductions in exposure everywhere in a regulatory jurisdiction, if you don't count those benefits at lower levels versus you do count them, it could have a huge difference in the input into your policy decision making, right? So there, and in many jurisdictions, there's a variety of exposure. There's people living in very high environments, but there are people living in cleaner environments, and there are benefits, health benefits of those people, for those people, if those reductions in those lower environments are made. So I think it can be a real big difference. The other thing that's interesting is that in at least the Western world, concentrations tend to be going down. And when people do cohort studies, they're always in the past, right, with higher concentrations. So a lot of these even large cohort studies don't have data at these very low levels. So going to places like Canada, or in the ELAPSE study, going to Norway, for instance, is really important to understand what that shape looks like at these low levels. It can have huge implications. And as Mike presented in our paper coming out, or it's in press now, that the modeling of these low concentrations can affect burden estimates in places like China and India. So I think it's quite important.
Good, thank you. Next, we have a question from Kelvin Fong, and asks whether the demographic profile, for example, age, play a big role in affecting your results. Sounds to me like an effect modification question. Does age or other demographic information influence the effect estimates?
So I don't remember all the details about age in terms of trying to explain the shapes on things. I think we definitely saw consistency across ages. Even we played around a lot with actually how age entered the model, so the different age strata. That certainly didn't explain the regional variation, and that didn't explain, we couldn't sort of get rid of those wiggles, the bumpiness in that by sort of looking at different approaches to age in the models. But yeah, I actually don't remember exactly what the sort of age relationships were, all the details. So we did look at different ages. Certainly, all those details are in the report. Rick, I don't know if you remember better.
Yeah, well, certainly in typical cohort studies, I think the subjects which were followed up over older ages, the relative risks were lower. Now, that's often explained by their baseline rates are much higher, mortality rates are much higher. I think we did see some sex differences. Unfortunately, I don't remember which way they went. We did look at effects by a number of things, by income, education, and of course, in large cohort studies, you can always find statistical differences between these groups. But
thank you. Next question is from Huaxin Xin, and was concerned really about the very narrow concentration range there and how sensitive the findings are to very small changes in PM 2.5, and then something you can't do, which is to speculate on what would happen if you extended the concentration range.
well, so one of the interesting things that we're finding in Canada and in the United States is, like I said, that even if the concentration range of PM 2.5 total mass, which is made up of usually these secondary inorganic aerosols that are driving that total mass, can be very small, but other low mass constituents can vary by orders of magnitude, basically because of specific point sources. So I think we're trying to understand, and I think everybody in the world is trying to understand that total mass isn't the right metric. It's a very useful metric, and we've used it for a long time now. But and we do have an ongoing project funded by HEI where we're looking at the transition metals and oxidative potential and sources and so on to try to understand how that mixture is affecting toxicity. With a spline model, of course, you have to talk about extrapolating above the way the shift model is made, because we're using these logarithmic functions, all extrapolations, even if the model looked linear within the concentration range, it would be extrapolated as a superlinear function. So that's one of the features of the model. And, you know, people will take these concentration response models and do all kinds of things with them. And they do things like, you know, they'll have a person in a very polluted city riding a bicycle, and they'll say, what's their total intake of particles? And it's like, of course, way above the data that we'd have in the concentration range. So there is actually a lot of interest in people using these functions to predict marginal changes in health way beyond the concentration range of the cohort.
Good. Thank you, Rick. Just on a related question, I'll jump ahead and then come back. You were talking about different metrics to be used. There is a question about using particle number as an exposure metric as opposed to mass. Whether you would comment on your perspective on that.
Thanks. I mean, I think one major challenge, and certainly in an analysis of this type, is really just estimating exposure. So a number of challenges. So keep in mind that we're trying to estimate exposure over 25 years for an entire country that's very, very large geographically. And so we need approaches to do that. For particle number, I don't know of any models that are capable of doing that. So that would mean you'd be restricted to measurements. And we essentially don't have those measurements. And even if we have those measurements, trying to backcast them over time would be extremely challenging. So we really don't have any ability to do that in kind of in a study of this size and this sort of temporal scope. And so one of the information that we do have about particle number really tends to come from very, very small studies that are restricted to sort of urban areas and looking at variation within urban areas. And I think that's challenging because that is also then reflects other pollutants as well. So it's not just particle number that would vary in that fashion.
Thank you. That was a question from Kevin Hedges, by the way. Next question is a question from Jillian Middlestadt, talking about future work and specifically focusing on causes of mortality and whether concerned or interested in whether there are different patterns of the concentration response function, for example, with different types of diseases, cardiovascular versus respiratory versus autoimmune, and whether that would be useful in terms of public health communication or interventions. So the main issue is really looking at differences by outcome.
Yeah, so we did provide all of those shapes and E-shifts for the different causes of mortality as well, and that all that detail is in the report. I would have to say, in general, for the major causes, so the cardiovascular causes and the major respiratory diseases, those patterns reflect what we showed for non-accidental mortality. But then if you get into diseases that are less common causes of death, the relationships differ. And I would say we didn't have a consistent story to tell. I think it's actually a great question, but it's complex because you could have in different parts of the country sort of different makeups of the population, different prevalences of these diseases and major causes of death. So I think that was an important learning note for me in this study, is that as pollution varies, the population can also vary as well. And so as you sort of slice and dice more finely, you're not really doing sort of apples to apples comparisons. So if you're comparing one population to another population, exposure may change, exposure characteristics may change, but that population may change as well. And we did a lot of work to try and make sure we were comparing like with like, but when you start really slicing and dicing in multiple ways, that becomes much more challenging. So I think that's where we really didn't see sort of, a consistent story that we could say, at this level, it was this disease, at this level, it was this disease. But perhaps that kind of relationship might exist. And Rick, I don't know if there's anything you'd like to add to that.
Yeah, so some of the work that isn't done funded by HEI, but I'll plug in funded by Health Canada, is the CanCheck cohorts have also been linked to hospital admission data, which we haven't used in this project, but other researchers at Health Canada have. And so trying to get at this disease progression idea of a healthy individual that is disease-free, has no diagnosis of certain diseases, then are being admitted to hospital, and then we're following those individuals through CanCheck to death. So the idea of, what role is air pollution playing in the development of the disease versus change in longevity, getting at that through sort of multi-state models and so on. So this sort of individual disease progression and how diseases interplay with each other is something that's really interesting to us, and we're trying to pursue.
Thank you. Giovanni Viegi has a question, and it relates to the apparent large differences in he says the concentration response function between the North American studies and the European one. I think put a finer point on it. I don't think it necessarily in the shape of the concentration response function, but it's in the hazard ratios at given concentrations. For example, in the European study, there are very large hazard ratios for concentrations that overlap with the Canadian studies, and the same with the Medicare data. The hazard ratios are somewhat larger. So I guess some comment or perspective perhaps on those differences, which may be challenging.
Yeah, one thing I would say, I know you're asking more about magnitude rather than shape. Something that I'll just share with you very briefly that we presented at the HEI conference is see if this is visible. This is a combined SHIP across CanCheck, the European cohorts, and Medicare cohort that Rick put together. And while there certainly is heterogeneity in the shapes, including heterogeneity within the European cohorts, overall, I would say there's a lot of consistency. So that, obviously they're not the same, and these are certainly different studies and in different locations over different time periods. But I think there is quite remarkable consistency considering that these are different studies. But going to magnitude, we don't know. We can just speculate, and some of the things would be, again, population distribution. So the different populations. Remember also that these studies are conducted over different time periods. So different follow-up periods, but also different eras. And they're also different. We have a nationally representative population. Medicare is those over 65. We've looked at age in a harmonized analysis that we've done, but there's all kinds of differences across the populations. In the harmonized work, we've also looked at a common exposure approach. So we've actually applied the MAPLE exposure assessment to Europe and to the US for Medicare. So try to adjust for all of those features. And yes, we still do see some differences, but it's really something we can only healthcare access is another, or not even access, but just healthcare differences in healthcare and how it's delivered across location, and as well as population structure. Rick, you can jump in. I'm sure you've got additional thoughts.
Yeah, well, one of the striking results is really with the escape cohorts, that have been under a lapse pooled together. And a lot of the contrast there is within metropolitan area. And we see, particularly in studies we've done in Canada, where with NO2, is we see this big difference, much larger effect estimates from within city studies as between city studies. And that gain, the most obvious thing, of course, is that low weight particles are driving the exposure contrast, which is correlated with a very small contrast in PM2.5. So if you have a small change in exposure in PM2.5, and it's really being driven by a huge change in exposure of low weight particles, then the PM2.5 hazard ratio is going to be very big, right? It's just scaled at the wrong scale. So I hate to keep coming back to this theme, but it's one that can explain a lot of things if only we could actually understand it better.
Thank you. A question from Aaron Cohen relates, I think, to something that Mike just showed, which is, did the Medicare and the lapse also see regional variations of the kind that you're seeing in Canada? Yeah, go ahead.
So 2 points. So one, yeah. So I did. So certainly, elapse. There's regional variation, but I would say there's also in elapse much more dramatic regional variation in magnitude as well. So even though we saw these differences in airshed, we're still talking about a very narrow range of PM2.5. Elapse, that range is much greater, but they definitely saw that. I don't believe Medicare has looked at regional variation, or I certainly haven't seen that kind of analysis. But as I think Rick showed, there is some wiggles in their sort of concentration response function as well. So it's not but that could be explored. Rick, anything to add?
Well, yeah, the Medicare concentration response is part of the harmonization project. So they use the same Randall-Martin exposure data, and we had the same covariates and the same modeling done on all three studies. And we're just finalizing a paper, which hopefully will be submitted soon on that. And in that one, you actually did see in that sort of 5 to 7 or 8 concentration range, a slight negative decline in the Medicare cohort, which we also saw in the CanCheck cohort. I don't know, that could be just coincidence and so on. I mean, early on in the American Cancer Society analysis, right, we saw negative effects in the West. And we see these huge positive effects in the sort of Ohio Valley region, right, in the United States. So, for decades now, we've known that the associations with PM2.5 and mortality can vary dramatically across locations.
Thank you. Question from Detlev Helmig, which I find to be an intriguing one. An interesting one, which is, he's referring to in the Colorado Front Range, they observe relatively modest long-term mean PM2 concentrations, but there are frequent episodes where PM increases for relatively short periods of time by a factor of from 5 to 25 or more, and that lasts from a few hours to minutes to hours, and comment on whether these short-term concentration spikes should be considered in health risk assessment. I guess the question here is, and I think it's an interesting one, is that in an area where you have 2 areas where you have mean concentrations that are the same, if one area has spikes in concentrations and the other area does not, would that be expected to have differences in health outcomes?
So that's a great question. I think it's one where many of us are grappling with now, sort of when we consider sources such as wildfire smoke and wildfire smoke episodes that are much more variable and certainly seasonal. So this study, we can't answer that, that question. We only looked at much longer term exposures. One of the things I did mention that we did compare would be, we looked at 1 year, 3 year, 8 year, and 10 year averages. And we tended to see stronger relationships and better model fits. We went to longer averaging periods in our analysis. But we're looking in a cohort design. We're not looking at short-term increases. Obviously, those short peaks can influence the long-term averages. So the more that you have, it's an interesting thought. Just thinking out loud here, that when we consider another feature of those regions, it's possible that it could be composition, but it also could be something about the temporality of exposure. So perhaps in those regions, that is more wildfire smoke or dust episodes that are more transient. In those regions where we didn't see the relationship, that is another possibility. We didn't evaluate it, directly.
You say you couldn't do that, but it's essentially a question of whether there's effect modification by this particular characteristic of this temporal characteristic of pollution. So it seems to be feasible. Your exposure models isn't going to be able to capture that, but in terms of regional differences, one might be able to characterize an area that has very marked changes in short-term changes in concentration versus an area that doesn't, and is approaching from an effect modification perspective.
Yeah, I think it's possible. I mean, we probably have to rely on the ground monitoring data, which is sort of spatially biased, because there's sampling issues with the satellite information, where we're not actually getting information every day. We're only getting information on a daily basis, not an hourly basis. So this sort of, but yeah, I think some, a spikiness metric or something like that we could think about developing something like that and testing that. I think it's really an interesting idea and an important one. Especially as I mentioned, where we're increasingly facing things like wildfire smoke episodes.
Yeah, just to add to that, Scott Weisenthal and his group used the CanCheck cohorts to link to a fire smoke model for exposure, and has looked at different outcomes, and in particular lung cancer. And so those two airsheds are, I think, more prone to forest fire and forest fire smoke exposure. So that's something that we haven't directly taken into account. Also, if the dose response is really nonlinear, these huge spikes could make a big difference. Cohort studies are designed in such a way that sort of the harvesting problems of these sort of spikes in the time series studies are averaged out. So, so if there isn't really a lot of harvesting issue in these daily fluctuations, and the dose response is nonlinear, you could see a big difference by adding in, daily exposures versus longer term exposures.
Thank you. There's a question from Tim Siselski, I think directed to Rick. He says, as you note, the shape of the spline can be strongly determined by the number of knots. To me, this suggests that we should usually start with 3 knot splines and not specify knot number or location. Make suggestions as to how to do that. Should this become standard practice as a first pass analysis, analogous to considering a scatter plot before running linear regression?
Well, so one of the reasons I wanted to show the smoothing spline that Francesca and her group produced is when you have these huge cohorts, right? Your best representation of even a smoothing spline can have all kinds of wiggles in it, and those little tiny wiggles that look Like, you think that doesn't really mean much on the relative risk axis when you look at that derivative of the PAF. They're huge oscillations. So, you know, you want to get, if you only, and in fact, number of people publish papers with lines with 3 knots or 4 knots. They look at 3, 4, or 5 knots and they say which is the best AIC or the lowest AIC or something. But you don't really know if that's the best representation in that particular data set. And that's the difficulty, you know, with that. So, you know, it's an option. And if you want to get smoother curves, I think it's a really good option. You just don't know whether that is going to end up as the real representation of the true concentration response in the data, right?
Right. Thank you. Here's another effect modification question. Does the PM concentration, the response function, differ between smokers and non-smokers?
So we did not look at that directly. We would have had to rely only on the Canadian Community Health Survey, so the 500,000 or so people. We did look at smoking, you know, in the phase 1 report. And I don't remember exactly, but in general, I don't think we saw strong differences in linear effects. And as you saw, you know, including smoking as well as the other behavioral risks in that survey really didn't attenuate the relationship. But we haven't looked at the shape of the relationship, and I'm not even sure of our abilities to do that, just given the small numbers there. Rick, do you want to add anything on that? Like,
yeah, well, I think that's one of the challenges, because the concentration range is so low. The National Health Survey, developing a cohort in the National Health Survey, only created over a decade of follow-up only 50,000 deaths. Now, the 6 City study, I think, had 8,000 deaths, and it did a lot, but the concentration range and exposure was huge. So we really only included the health survey, the CCHS, as this sensitivity analysis for inclusion or not inclusion of, I think, 6 behavioral covariates. So all these sub-analyses are, from an inferential point of view, very challenging, because the uncertainty is so large. As you start to split the cohort up, you're not really getting an informative analysis. So that's why we really, you know, wanted to stick with the CanCheck cohorts.
Okay, there aren't any other questions from the audience. I would ask either Sarah or Ben, or I could ask one additional question, unless we're running out of time. I'll leave that up to you.
We have about a minute more.
Well, I wanted to ask a question about the lung cancer issue. So this is a low concentration exposure study. And, you know, as you noted, Mike, other studies have found associations with lung cancer, but presumably one would think that the mechanism of disease causation differs between lung cancer or other cancers, say, and cardiovascular outcomes or respiratory outcomes, and whether one might not expect a lung cancer association at very low concentrations in light of the potential differences in mechanism.
It sounds reasonable. You know, I mean, it's also, really nothing to say there. Yeah, I think it's possible. We've also, I'd say, in other analyses in CanCheck, we have seen associations with lung cancer, so it's rather puzzling. One of the things that we will be doing in the near future is we have 2 additional cohorts, so 2 additional CanCheck waves, and I'd like to look at cohort effects and see if there have been changes. So perhaps, so both looking at sort of latency, but also looking at, you know, have there been changes in lung cancer mortality that you know, may, in terms of treatment, that may have changed over time, or other risk factors. So those are all, you know, anything sort of open, but you know, it was puzzling to us, and I don't think we really had any we, you know, hit our heads against the wall a bit, but really couldn't come up with any explanations.
Thank you.
I'd like to thank all our participants today on the webinar, and especially our web audience. Please note that the recording will be posted on our website, and please visit our website where you can freely download a copy of the report and the commentary from the peer review panel. And I wish everyone a good rest of your day. Thank you.